Section: Introduction. In this section, we discuss the advancements in video large language models, VLLMs, driven by the development of multimodal large language models, LLMs. Unlike single images, VLLMs need to encode each video frame separately, which leads to generating many visual tokens, even from just a few sampled frames. While some methods aim to reduce these tokens through network design or trainable modules, they often come with extra training costs and limited portability due to their complex structures. Thus, we see the need for training free token reduction strategies during inference to enhance video processing efficiency. One common approach for reducing tokens is selecting the most representative ones. Previous methods for image token compression typically use attention scores to find important tokens. However, these attention-based methods often focus only on key objects, which can lead to missing out on a complete representation of the video's semantics and repeating key elements. To address this, we propose the Semantic Connected Components (SCC) strategy. SCC measures the similarity between tokens to group them into distinct, non-overlapping regions, capturing all unique semantic areas without needing tokens to be adjacent. This allows us to represent video content more comprehensively and efficiently. Recognizing that image-based methods do not account for temporal redundancy in video frames, some strategies have started to focus on video-specific compression. These often segment the video and compress tokens either between segments or based on fixed pixel positions over time. However, they fail to consider that semantically similar regions might not be temporally connected, leading to redundancy. To overcome this, we introduce LLaVA-Scissor, a two-step spatio-temporal token compression method that utilizes SCC. First, we identify unique semantic regions in each video frame's spatial domain. Then, we apply SCC again to eliminate temporal redundancy across frames, resulting in a refined set of tokens that effectively represent the entire video without redundancy, capturing distinct semantic information from both spatial and temporal angles. We evaluate LLaVA-Scissor on various video question answering and understanding benchmarks, using the enhanced LLaVA-1 vision model as our base. Our results show that LLaVA-Scissor consistently outperforms other token compression methods, especially at lower token retention ratios. We also analyze how performance changes with different token retention ratios, confirming that video token redundancy exists and that our method is more effective at preserving key semantics, leading to better performance. In summary, we highlight that existing attention score-based methods do not fully capture the entire token set and introduce the SCC strategy for token compression. We present LLaVA-Scissor, designed specifically for video LLMs, which provides a more efficient representation of video content. Our experiments demonstrate that LLaVA-Scissor surpasses other token compression techniques across various benchmarks. Section Summary. In this section, we discuss the advancements in video large language models, VLLMs, and the challenges of token reduction due to the high number of visual tokens generated from video frames. We introduce our Semantic Connected Components (SCC) strategy and the LLaVA-Scissor method, which effectively compress tokens by capturing distinct semantic regions across both spatial and temporal dimensions, leading to improved performance in video understanding benchmarks. Section: LLaVA-Scissor. In this section, we introduce the Semantic Connected Components (SCC) method to identify different semantic areas within a set of tokens by using connected components. We then outline a two-step process that applies the SCC approach in both spatial and temporal contexts to effectively compress tokens for video understanding. For token compression using SCC, we notice that previous methods often select overlapping semantic areas while missing others, which complicates the creation of a representative token set. Our approach aims to identify all unique semantic regions and keep one token for each. We start with a set of tokens and calculate the similarity between each pair, creating a binary map that shows which tokens are similar based on a set threshold. This binary map acts like a graph where each token is a vertex, and we can find unique semantic regions by identifying connected components in this graph. To do this, we use an approximate method. We sample a subset of vertices from the total based on an error tolerance. For each sampled vertex, we find its neighbors and use a union-find structure to identify connected components. If some vertices are not covered by the sampled vertices, we treat each of those as separate components. We then sort these components to maintain the relative positions of the tokens. The sorted components represent distinct semantic regions, allowing us to compress the original token set by aggregating tokens within each component, resulting in a new, smaller set of tokens. Next, we apply the SCC strategy in a two-step process for token compression across both spatial and temporal dimensions. For a video made up of multiple frames, we derive visual tokens from each frame using a visual encoder. We first find representative tokens for each frame, then combine these tokens to address redundancy across frames. Since similar semantic regions may appear in multiple frames, we apply the SCC strategy again to compress these representative tokens further, ensuring that the final set of tokens captures all distinct semantic regions without overlap. Finally, we select the most relevant semantic regions for all tokens. We compute a similarity map to find the closest representative token for each source token and merge them to create the final compressed token set, which effectively represents the entire video. Section Summary. In this section, we propose the Semantic Connected Components (SCC) approach to identify unique semantic regions within a token set, enabling effective token compression for video understanding. We implement a two-step strategy that first compresses tokens spatially by retaining representative tokens for each frame, and then further compresses them temporally to eliminate redundancy across frames, resulting in a comprehensive set of distinct semantic tokens for the entire video. Section: Experiment Setup. In this section, we outline our experiment setup and implementation details. We start with LLaVA-1 Vision as our base model, which uses CLIP for visual encoding and Qwen2 as the language model. However, due to the rapid progress in multimodal language models, we recognize that this architecture is not the most advanced anymore. We replace the visual encoder with SIGLIP, which is considered superior, and upgrade to Qwen 2.5 for the language model. We then retrain an improved version of LLaVA-1 Vision using open-source Oryx data. With this enhanced model, we implement our proposed method and conduct comparisons with other approaches to ensure fairness. We mainly control the retention ratio using a similarity threshold, which we set to a specific value unless stated otherwise. All our evaluation experiments are performed on a single NVIDIA A100 GPU. For benchmarks, we test LLaVA-Scissor across various tasks, including video question answering and long video understanding benchmarks, as well as the comprehensive multi-choice benchmark MV-Bench. We provide detailed descriptions of each dataset in the appendix. We compare our method against several notable open-source methods, including VisionZip, PLLaVA, FastV, and DieCoke, with specific settings for token ratios and attention layers as per the original papers. In our results, we find that on video question answering benchmarks, while all methods perform similarly at a 50% retention ratio, LLaVA-Scissor shows increasing advantages as the retention ratio decreases, indicating its effectiveness in maintaining essential information. For long video understanding benchmarks, LLaVA-Scissor consistently outperforms other methods, especially under low token budgets, achieving better results at a 5% retention ratio compared to others at 10%. We also evaluate LLaVA-Scissor on MV-Bench, where it surpasses all other methods at both 35% and 10% retention ratios, showcasing its consistent superiority across various tasks. In our ablation study, we examine the effectiveness of different components of our method, maintaining a 35% retention ratio for fairness. We find that using only spatial compression is less effective due to redundancy, while our two-step compression method, which removes temporal repetition, yields better results. Additionally, merging tokens with selected representatives enhances performance. We also assess our token selection strategy, SCC, against other methods like random and uniform sampling, as well as L2 norm for higher information density. Our results show that SCC outperforms these alternatives. Finally, we analyze the impact of the similarity threshold and error tolerance on token numbers after compression. We observe that a more lenient threshold allows for more tokens to be compressed, and the number of tokens varies across benchmarks. The error tolerance serves as a trade-off between accuracy and efficiency, with our findings indicating that setting it to 0.05 effectively identifies and merges distinct semantic regions. Section Summary. In this section, we describe our experimental setup using an enhanced LLaVA-1 vision model, where we replace the original vision encoder with SIGLIT and upgrade the LLM to Qwen 2.5, allowing us to evaluate our method, LLaVA-Scissor, against various benchmarks and compare its performance with other compression strategies, demonstrating its superior efficiency in preserving semantic information, especially under low token retention ratios. Section: Efficiency Analysis. In this section, we analyze the efficiency of our approach. Following DICOC, we break down the floating point operations, or flops, during the large language model, LLM, stage into two phases: the prefilling stage and the decoding stage. In the prefilling stage, the computational cost for each transformer layer involves multi-head attention and feed-forward networks, which we can express in simpler terms as a combination of factors related to the number of tokens, hidden state size, and intermediate size of the feed-forward network. During the decoding stage, we benefit from the key value cache, which significantly lowers the computational cost for decoding each token. We represent this cost as a combination of terms involving the hidden state size and the number of tokens. For our calculations, we set the number of transformer layers to 100. We also calculate the flops introduced by our LLaVA-Scissor during token compression. The main computational cost arises from comparing tokens, and we express the flops generated by LLaVA-Scissor in terms of the number of frames, tokens per frame, and hidden state size, along with the number of tokens after each compression step. In our comparisons, we look at flops and average performance across various benchmarks, contrasting our method with others at different retention ratios. Unlike FastV, which compresses tokens during the LLM stage, our LLaVA-Scissor compresses tokens beforehand, leading to a significant reduction in flops. We consistently achieve the highest average performance at the same retention ratio, particularly when the retention ratio is low, outperforming methods like PLLaVA and Vision Zip. We observe a trend in token compression. When the retention ratio is high, existing methods, including LLaVA-Scissor, maintain model performance well. However, as the retention ratio decreases, performance declines sharply. To understand this better, we analyze the relationship between retained token numbers and performance. In our comparative analysis of different models on benchmarks like MVBench and Video MME, we find that most token reduction methods maintain performance close to the original model, even with a naive sampling strategy. This suggests a high level of redundancy among visual tokens in video language models, indicating that many tokens contribute little to predictions and can be discarded without major impact. We also evaluate the performance drop of various token selection methods under aggressive token retention ratios. Unlike previous results, we see a significant decline in performance when the retention ratio falls below 35%. This indicates that indiscriminate token reduction at low budgets leads to the loss of important visual information, hindering model understanding. Notably, our LLaVA-Scissor shows consistent superiority, especially at a 3% retention ratio, where it retains a higher average score compared to FastV. This highlights our method's ability to prioritize semantically important and diverse tokens while reducing redundancy, making it more effective for tight token budgets and preserving essential visual semantics for accurate video language understanding.